Okay, good morning friends. This is the continuation of EDC lecture 2. In EDC lecture 1, you have see the semiconductor physics. In that first 5 questions you are completed. So this is the 5th question. You got the 5000 for answer this. So from next onwards, you are going to see the 6th question. The units of Q by KT are units of K by QT are. See the solution. You know that thermal voltage. This is the formula for thermal voltage. Thermal voltage is equal to KT by Q. That means voltage means units are volts. Here he asked that reverse Q by KT. He is not asking the KT by Q. If KT by Q he asked that, then the units are volts. He is asked that Q by KT. So Q by KT inverse of voltage is the units. He asked that what are the units for Q by KT. So answer is volt inverse. So similarly, next move to the second question. 7th, the intrinsic carrier concentration of silicon sample at 300 Kelvin. That means this is the room temperature 300 Kelvin is 1.5 into 10 power 16. What he gave? Intrinsic carrier concentration. That means he gave that Ni he gave. After doping the number of majority carriers is, this is the majority carriers, either Nd or Na. Take the N or P. He gave that anyone, N or P, and Ni he gave. The minority carrier density he want. So you all know law of mass action, Np is equal to Ni square. Here he gave either N or P. Take it as either N or P. If it is majority, the other one is minority carrier. He asked that minority carrier density. So find any one, nothing problem. So Ni he gave already, Ni square by either P or N, other element make it by Ni. So 5 into 10 power 20. If you simplify this, you get the answer as 4.5 into 10 power 11. So actually 45 into 10 power 11 you got. But the answer is in this form, so you can convert this as 4.5 into 10 power 11 per meter cube. Here units also important. So next move to the 8th question. The band gap of silicon at 300 Kelvin is. So this is the important question. The band gap of silicon at 300 Kelvin at room temperature. Here you have two types of band gaps, at 0 kelvins and 300 kelvins. At 0 kelvins 1.21 is the 1.21 electron volts at 0 Kelvin. This is, he asked at 300 Kelvin means 1.10 electron volt. This is the answer. So see the question. So, silicon at 300 kelvins 1.1 electron volts. 0 kelvins 1.21 electron volts. He asked at 300 kelvins means 1.1 electron volts. Similarly, if you see the germanium also, for germanium 0.785 at 0 Kelvin. Remember this, germanium at 0 Kelvin 0.785. What about at room temperature? 0.72 electron volts. Here also electron volts. This is at room temperature 300 kelvins. 0.70 electron volts for germanium at room temperature, 0 Kelvin 0.785. So remember this, important. Next move to the 9th question. N-type silicon is obtained by doping silicon with. N-type means this is a donor type. Here you want to have the one extra electron, that is free electron, where you are going to get free electron from all these elements, germanium, aluminum, boron. All these are trivalent atoms. Only pentavalent atom is phosphorus. You want to get N-type from semiconductor, you want to add pentavalent. Pentavalent means phosphorus element is the answer. So see the how the bonding is formed. Phosphorus have 5 electrons in its valency. So each silicon has 4 valence electrons. So every phosphorus, each electron forms a covalent bond with the silicon. 4 electrons silicon bonds, but phosphorus has 5 electrons. So 1 electron is free in phosphorus. This is the reason for conduction in the N-type semiconductor. So this is the free electron. So this type of bonding is formed. So N-type is obtained by doping the fifth group element, that is phosphorus, gallium, indium, phosphorus, and remaining elements, fifth group elements you want to add. 10th question. If he asked that p-type silicon, then boron is the answer. This is trivalent atom. This is the pentavalent atom. Okay. 10th question. The impurity commonly used for realizing the base region of a silicon NPN transistor is. So base region means P. The impurity, what type of impurity you are going to add for p-type. So here is indirectly asked that for p-type semiconductor what impurity you are used. So just before I said in this question, for N-type you are using phosphorus, for p-type you are using boron. This is trivalent atom. For boron you are going to add doping to the p to get the p-type. So he asked that base, that is in P. Base means P. For P you are going to add boron. That is the answer. If phosphorus for N-type. Okay, next move to the 11th question. The primary reason for the widespread use of silicon in semiconductor device technology is why you are used widely in semiconductor silicon, because its abundance of silicon on the surface. This is also one reason. Larger band gap of silicon in comparison to germanium. Our reason must be genuine. Because of abundance of silicon we are using, that is not the correct reason. It must be some technical reason, and it must satisfy some parameters, theoretical and everything. So larger band gap of silicon in comparison to germanium. This is the answer. Larger band gap you have in silicon rather than remaining all semiconductor elements. So see the solution. 11th question. Silicon band gap is greater than germanium band gap. You observe this. Silicon band gap is 1.21 electron volts at 0 Kelvin, and at 300 Kelvin 1.1 electron volts. But in germanium 0.785 electron volts. So silicon has larger band gap rather than germanium. What is the use of if band gap is more? Oh, I will tell in coming lectures. Having the band gap large is some advantages you have. If you have the smaller band gap, there is a problem for getting conductivity and maintaining that state. That is the problem. That's why you are choose silicon rather than germanium. Nowadays germanium also widely using. The reasons you will see in the coming problems. Yeah, next 12, 13, 14 I will tell you later. 15, see the 15th question. What he asked that the concentration of minority carriers in an extrinsic semiconductor under equilibrium is. The concentration of minority carriers in an extrinsic semiconductor under equilibrium is. What happens to the extrinsic semiconductor minority carriers? Okay, see the concentration of minority carriers in extrinsic semiconductor. See the solution. You know that Np is equal to Ni square. If you are in extrinsic semiconductor, what you did for getting N-type, you are going to doping the with P-type elements. So while doping for N-type, as number of electrons increases, holes decreases. Number of electrons increases, holes decreases. If you want to get P-type extrinsic semiconductor, this is extrinsic semiconductor, this is also extrinsic semiconductor. You want to get extrinsic semiconductor while adding electrons, that means N-type, you are decreasing the holes. Similarly, if you want to get P-type, you are increasing the holes, then other side electrons will decrease. So what is the relation? One increases, one decreases. This is the inversely proportional. So majority carriers, minority carriers, there is the relation we have as inversely proportional. So choose the answer. Inversely proportional to the doping concentration. Inversely proportional to the intrinsic carrier concentration cause not the answer. Directly the inversely proportional to the doping concentration. As doping concentration increases, electrons increase. What about holes decrease? As doping concentration of holes increases, electrons decreases. So this is the relation inversely proportional. Next, move to the 16th question. The electron and hole concentration in an intrinsic semiconductor are Ni per centimeter cube at 300 Kelvin. Now if accept our impurities are concentration of Na per centimeter cube, the electron concentration per centimeter, this is nothing but he gave that Ni and he gave Na as acceptor impurities. What about he asked electron concentration? That means he asking Nd. Nothing is here new to us. So till now you are seeing the Np is equal to mass action law. Np is equal to Ni square. N means Nd. P means Na. This is the acceptor. This is the acceptor impurity atoms. This is the donor impurity atom. So N is equal to Ni square by P. P means Na. He gave that. He asked this one. So from options, Ni square by Na is the answer. Okay, move to the 17th. Which of the following is true? A silicon wafer heavily doped with P plus substrate. A silicon wafer lightly doped with boron is. So see the four options. He gave that heavily doped means P plus. Lightly doped P plus not the correct. Heavily doped P plus okay. Lightly doped P plus, this is not the correct. So A or C is our answer. A silicon wafer heavily doped with a P plus substrate. A silicon wafer heavily doped with arsenic. Arsenic you are not used. Silicon you are widely using. You all know. So a silicon wafer heavily doped with is a P plus substrate. Boron, yeah. For P-type, what you are doping? Boron. Yes. For P-type, you are doping boron only. That's why the answer is A. You are not using arsenic for P-type semiconductor. The answer is A. So move to the 18th question. In an N-type silicon crystal at room temperature, which of the following can have a concentration of 4 into 10 power 19? So he gave this value. What is the value related to options? Silicon atoms, holes, dopant atoms, valence electrons. If you know all these concentration density values, then only you can answer this. So silicon atoms per centimeter cube, holes per centimeter cube, dopant atoms per centimeter cube, valence electrons per centimeter. That is he asked the density of the atoms. What about the density of silicon atoms? And if you know the values, if you standard values, then only you can answer for this. So see the solution. He asked the number of silicon atoms per centimeter cube, This is the 5 into 10 power 22. Number of holes 1.5 into 10 power 10. Number of valency electrons 4 into 10 power 23. What he asked that 18th question. He gave already 4 into 10 power 19. This is related to dopant atoms. So the answer is C. So drift current in semiconductor depends upon. So you already seen that drift current about. Here he asked that drift velocity of electron is silicon. So here also one more question on drift current. Drift current semiconductor depends on both the electric field and the carrier concentration. What is drift current? When you are increasing the electric field, the number of carriers increases, so that electric field also increases. So drift current depends on both electric field and the number of carrier concentration. So answer is C. Move to the next question 20. A silicon bar is doped with the donor impurities Nd he gave. Given the intrinsic carrier concentration Ni he gave that, assuming complete impurity ionization, the equilibrium electron and hole concentration. Similarly, here is also known U to us. You know Np is equal to Ni square. He gave 1 Nd, he gave Ni. So the equilibrium electron and hole concentrations. He already gave this as a electron concentration, that means 2.25. Our first option, you want to get P. You know Np is equal to Ni square. From that you want to get P. P0 we get as 1 into 10 power 5. See the solution. Nd is equal to 2.25 into 10 power 15. He gave everything. He asked that equilibrium. Equilibrium means at 0 kelvins. N0, P0 are complementary. Complete. He gave one word, completely. Complete impurity ionization means all the electrons while you are doping, these all the enter into the conduction band. These all the electrons enter into the conduction band. This is the completely ionized, complete impurity ionization. Complete impurity ionization means these doping electrons are entering into the conduction band completely. So at that state, what is the number of electrons? Is equal to, he gave that this is the equal to Nd, so 2.25. Here all the electrons what you are doping enter into the conduction band only, so this is equal, Nd is equal to N0 or not? Okay, N0. So this is N0. You want to get P0. So P0, you know Np is equal to Ni square. From that P0 is equal to 10 power 15, 10 power 5, 20 minus 15, 5, 10 power 5. Okay, move to the 21. A thin P-type silicon sample is uniformly illuminated with light which generates excess carrier. The recombination rate is directly proportional to. Here, see the answer, conceptual question. A thin P-type silicon sample is uniformly illuminated with light which generates excess carrier. The recombination rate is directly. Actually, this concept is related to diffusion, and diffusion problems we will solve in next. Of course, you will see the recombination rate and excess. Recombination rate is directly proportional to. He asked that. You know the formula. Recombination rate is equal to delta n by tau. This is the carrier lifetime. Delta n means excess minority carriers. So recombination rate is directly proportional to excess minority carriers and inversely proportional to carrier lifetime. So recombination rate is directly proportional to excess minority carriers. See the options. Excess minority carrier concentration is directly proportional. Answer is D. Move to the 22nd. At T is equal to 300 kelvins, the whole mobility of a semiconductor μp he gave that, kT by q he gave that, the whole diffusion constant dp. On the diffusion problems I will solve later. because diffusion is a very important concept. From last 6 years he asked that 10 to 12 questions. So every question from this basic concepts of semiconductor physics he is concentrating on diffusion only. So diffusion very important. On diffusion all the questions solved at one time, so that we can understood easily what is diffusion, and it's important, very important topic, diffusion. Recently he is asking from last 5 years questions on diffusion only. So remember that. Move to the 23rd question. At T equal 300 Kelvin, band gap, and he gave that band gap energy and intrinsic carrier concentration. So what he asked, lambda c, cutoff wavelength he asked. He is asking that cutoff wavelength. What is the cutoff wavelength? He asked Planck's, he gave Planck's constant also. So lambda c you want to find cutoff wavelength. See the solution. So if you want to get the diffusion, here incident light must be incident light energy must be greater than or equal to energy band gap. Here, so if you want to get the diffusion, incident light is greater than or equal to energy band gap of existing. So Eg is inversely proportional to bandwidth. See the Eg is equal to 1.24 by lambda micro electron volts. This is the formula. So minimum energy should be Eg. Maximum you can apply anywhere, but minimum it should be Eg or greater than Eg. So minimum, that means Eg minimum is equal to 1.24 by lambda. This is minimum means this is maximum, inversely proportional now. Okay. You want to get lambda max is equal to 1.24 by Eg minimum. Eg he already gave 1.42 electron volts. So if you read the simplification, 0.873 micrometers, you get lambda c maximum. That means lambda c maximum 0.873 micrometers. See the options. 0.87 micrometers maximum. So minimum it must be included, and maximum 0.87 micrometers. There is no other option. So option A is correct. Next, move to the 24th question. With the band gap, he gave on graph, and the resistivity. He gave ln of resistivity is plotted. Resistivity versus inverse of temperature. So resistivity and temperature, it gives what is the value. He asked that. See the solution. Temperature based only energy gap and intrinsic carrier concentration. Only energy band gap and intrinsic carrier concentration are depends on temperature. One of these two are options from the. See the options: band gap energy or intrinsic carrier concentration only. Our answers, because mobility did not change with temperature. Mobility is constant for electron and holes. So A and D are our answer. In that, only one answer we want to choose. Band gap energy of silicon, intrinsic carrier concentration also for silicon, 1.5 into 10 power 20. This is also constant. So band gap energy of silicon is the answer. As temperature increases, band gap increases or decreases? Increases. So band gap of Eg. Answer. Our answer, band gap energy. 25. See the 25th question. As you just now you solved on wavelength and energy band gap. Here he gave that impurities, donor impurities Nd he gave, and electron and hole mobilities. This is electron mobility and hole mobility. Assume complete ionization of impurities. The charge of an electron, the resistivity. Resistivity, he asked that rho. Rho means 1 by sigma. You know sigma formula, nq mu n. He asked rho resistivity. Rho means 1 by sigma n. You know the nq mu n as formula for conductivity. So nq mu n, he gave n as donor impurity, and q, you know, charge of the electron, and mu n, mobility of the electron, he gave 1200. If you simplify 0.52, you get the answer. So this is the 26th question. Next move to the 27 is also diffusion. So move to the 28th question. And diffusion problems I will solve later, all at a one time. A piece of silicon is doped uniformly with phosphorus with a doping concentration of 10 power 16 per centimeter cube. So doping concentration he gave the expected value of mobility versus doping concentration of silicon assuming full. The charge of electron he gave the conductivities. Here in the above problem he asked resistivity, that is reciprocal of conductivity. Here he is asking that conductivity, that means sigma n. He is asking sigma n. For sigma n, what we have to do? Formula, what is the formula? nq mu n. You know n, that means nd. Doping concentration he gave. Q, you know. Mu, you want to get mu. For mu, he gave one graph. From this you want to get the mu value. This is the doping concentration and this is the mobility, not 10 volt. This is the mobility I think, mobility. And he gave what is the concentration? 10 power 16, na? 16. 10 power, at 10 power 16, what is the mobility? That value you want to choose. He gave in the question the expected value of mobility versus doping concentration for silicon assuming full dopant ionization is shown below. He gave that. So that's why that corresponding mobility for this concentration 10 power 16, 1.e plus 16 means exponential of 16, that means 10 power 16. For 10 power 16 relevant to the mobility value is the mobility 1200. This is the 10 power 16, 10 power 16, this is 10 power 16 value, this is 10 power 17, that's why 1200 for mu n. So you have the everything, you have n, you have q, you have mu n. If you solve the, then you will get the 1.92. Here units are ohm centimeter inverse. Ohm centimeter inverse. Move to the next question, 29th question. Very important conceptual question. A small percentage of impurity is added to an intrinsic semiconductor at 300 Kelvin. Which one of the following statement is true for the energy band diagram shown in the figure? A small percentage of impurity is added to an intrinsic semiconductor at 300 Kelvin. Which one of the following statement is true for the? He gave the figure. From this figure, you conclude that energy, Fermi energy level is near to conduction band. See the figure. Fermi energy level is near to the conduction band and it is far away from valency band. This is the near to conduction band. What type of material it is? N-type material. Okay. For N-type, this is the N-type material because Fermi energy level is near to conduction band, away from the valency band. If this Fermi level energy is near to valency band, then what type of material it is? P-type. So here it is the N-type material. What he asked? Intrinsic semiconductor doped with pentavalent atoms to form N-type. Okay, to form N-type, you are adding pentavalent. Okay. Intrinsic semiconductor doped trivalent or not the answer. Intrinsic semiconductor doped with pentavalent. Pentavalent P-type is not you are adding. Pentavalent for getting N-type semiconductor, not for P-type. So this is not our answer. This is not our answer. If you are adding the trivalent, you are getting P-type, not the N-type. So D, observe D. Intrinsic semiconductor doped with trivalent atoms to form P-type. Intrinsic semiconductor doped with trivalent atom to form p-type. This is also correct, but from the given figure, what type of material it is? N-type material. So p-type not the correct answer. N-type material is the correct answer. That is the option A is the correct. So move to the. This is also from the diffusion. That's why I am told that recently he is concentrating on diffusion problem. That's why I will tell you later all the diffusion questions at one time. So this is also on diffusion. Move to the next question, 31. A bar of gallium arsenide is doped with silicon such that the silicon atoms occupy gallium and arsenic sites in the gallium arsenic crystal. Which one of the following statement is true? See the options very clearly. This is also one of the important conceptual question. A bar of gallium arsenide is doped with. Here he is not doping the silicon, germanium, actually pentavalent, trivalent. Here he asking that gallium arsenide is doped with silicon such that the silicon atoms occupy gallium and arsenic. So gallium arsenide is doped with silicon. See the options, very important question, conceptual. Gallium arsenide, silicon atom acts as. Okay, for gallium and arsenide, silicon, how it behaves, either N-type or P-type, he asked from the options. For gallium, what it behavior, for arsenide, what it behaves. Actually, silicon valency, what is silicon valency? 4 electrons. For gallium valency, 5. For gallium, boron, aluminum, gallium, this is trivalent atom. Trivalent means it wants 1 electron. So it has 4 electrons, it has 3 electrons. So this is donor for this gallium. For donor, what type of material you are getting? N-type. So silicon acts as N-type for gallium. For arsenide it has 5 electrons in its valency, but silicon has 4 electrons in its valency. So silicon wants 1 electron, or silicon wants 1 electron more. It has only 4 electrons, but it has 5 electrons. So here this is the donor, but this is the acceptor. So here for acceptor it acts like a p-type, and it is a donor for this gallium. So at this time it acts as a donor, that means p-type, N-type. So for gallium, silicon acts as N-type. For arsenide, silicon acts as p-type. See the answer. P dopants to in arsenic and N-type dopants in gallium. So this is the answer. Option A is the correct option. Go move to the. This is also on diffusion. I will solve the later. Last question today. Which one of the following options describes correctly the equilibrium band diagram at T is equal 300 Kelvin of a silicon Pn N plus P plus plus configuration shown in the figure? See the clearly, very important question. I will not solve this. I will give you as homework to you. Next tomorrow or day after tomorrow I will tell you clearly. I know the answer, but very conceptual and very important question. Which one of the following options? He gave 4 figures. See the 4 figures, A, B, C, D. He gave 4 options. From this, what he asked, at T is equal 300 Kelvin of a silicon Pn plus P plus plus configuration shown in the figure. Pn means this is moderately doped, this is heavily doped, this is degenerative. That means more heavily doped. That means degenerative. You call it as degenerative. That means more than heavily doped it was doping. So P plus plus. Then if you have this, what happened to the conduction band? What happened to the conduction band, Fermi level and valency band? He asked the how the behavior of conduction energy level and Fermi energy level and valency energy level. He asked the which one is the correct. You know the answer. Very important question. At 300 Kelvin he gave. That was also important. At 300 Kelvin, that means at room temperature, what is the behavior of conduction energy level, Fermi level energy level, and similarly valency energy level. So N plus, this is heavily doped, this is heavily doped, that means you are called as degenerative. P plus plus, this is degenerative. At this type, he asked here, he doped more P plus plus material. So P plus plus, where it was near to, which band it is near, for N-type which band it is near. Please choose the correct answer. Very good question, and we will give the answer in next video. Okay, thank you friends. Please subscribe for more videos, and I will solve gate problems daily. I will upload my videos. If you have any doubts or any mistakes in my concepts, please comment and refer to your friends also. Thank you friends. Thank you.